Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. What's new in the world of science then, Chris?
It was quite an interesting story that's come out this week. It's been published in the journal Child Development. This is Lawrence Steinberg and his colleagues. He's based at Temple University in America. And he's been trying to understand why teenagers have such a hard time when they're growing up. And it's all to do with how the brain develops. He quizzed 900 10 to 30-year-olds and he used tests, which are psychological tests, which included things called delay discounting tasks. The idea of these tasks is to try to work out whether people are very good at predicting and planning for the future. In other words, if I say to you, I'll give you £1,000 now, or if you wait a year, I'll give you £2,000, which one do you want? What you can find is some people are much more impulsive and they'll say, I'll have the money up front now, I'll have a short-term reward, a smaller reward, which I can have now, rather than have to wait for a bigger reward later. And teenagers classically seem to do that in his study. So it looks like that they have this kind of hyperactive thrill centre in their brains, is what he's saying. And at the same time, the self-control centre is struggling to contain this overactive thrill-seeking centre, and as a result, they tend to get a bit outlandish sometimes. But what's interesting is that the brain's self-control centres, which usually get blamed as being dysfunctional in teenagers, they're all intact and all working properly by the age of 16. It's actually trying to rein in this thrill-seeking behaviour, which takes a little bit longer to settle down and continues to develop after the age of 16. At least that's what their studies show. Why they say it's important is that when you're planning things like legal proceedings, or you're planning how to teach, educate, or perhaps to demonstrate things to younger people, you can't assume that they are going to think the same way as an adult. So a TV campaign designed to encourage people to, for instance, have safe sex, the same message that hits home and makes an impression on an adult may not work in the same way in a younger person. And so what Lawrence Steinberg and his colleagues are pointing out is that you have to take this into account when you're planning how you're going to engage with the younger person, because they at the same time may not be seeing the relevance that you see when you see a message.
All comes down to experience. Time now for Dr. Chris to answer your science questions. Dr. Chris, Andrew in Cambridge has asked about the electric trains. How much voltage and current are involved when they travel? And I think it means with the electricity, with the little hook that's on the overhead rails.
Yeah, the name for the pickup on an electric train is a pantograph. And this is the thing that slides along on the overhead cables. But trains fall into a number of different categories. There are the trains that you might jump on the station at Cambridge and go down the rail to London on. Those electric trains, those are the ones that are picking up power from overhead cables, and they tend to run on AC voltages, which are much higher, very, very high voltage. But when you get on the London Underground, when you arrive at King's Cross and you want to go across London, you'll inevitably be on an underground train that's using a much lower voltage, and it's also DC. So it's interesting, and there's a very good physical reason why this is chosen. DC voltage on the London Underground is about 600 volts, and the benefits of DC motors are that you can get very good control of the speed of the motor, so it makes the train ride very smooth. Also, they're very high torque, so when the train's trying to pull away from doing lots of pulling away with heavy loads on board, which underground trains make lots of stop-start type journeys, that kind of thing is very useful to them. DC motors are very good for that. And also they can be used for braking. So, for instance, you can connect the wheels to the motor and turn the motor into a kind of generator, and you lose some energy that way. And so on some train systems, you can use it to slow the train down very smoothly as well and scavenge some energy back. So that's why they tend to do that. Also, the reason for using DC at a lower voltage is that it's going to be a lot safer than AC. And when you've got exposed rails like that closer to people, it means that it's inherently a bit safer. The downside of using a DC lower voltage supply like that is that the current has to be a lot higher, because there's a relationship between the power that you're trying to get into the train and how much current has to flow. And the power that the train is exerting, the wattage, if you like, of the electric motors on the train, is directly proportional to the current that it's drawing. So if you put the voltage down, to get the same amount of power out, you've got to put the current up by the same proportion. And so the current that has to flow is therefore going to be a lot higher. Now, when you're on a very long train journey, very long train track, if you had those kind of transmission of those kind of voltages over those kind of distances with those kind of currents, the amount of energy you're losing in a supply rail is proportional to the current squared. The equation is P for power equals I, current squared, times R, the resistance. So if you have a very high current flowing, you will lose a huge amount of power because of the resistance of the cabling, turning that into heat. So that's why when you have very long train tracks and you do longer journeys, you use overhead cables, which are overhead because they're a lot safer. You transmit AC power at very high voltage because then you have to run a smaller current, and if you run a smaller current you waste less energy. So it's very useful and safe on smaller rails that you can easily sort of top up the rail every so often on an underground train, but on long distances such as overground trains, much better to have AC at very high voltage, but that means you use overhead cables, so it's a lot safer.
Excellent. Thank you, Dr. Chris. Now, staying with some electricity, Tesco Tom has asked, why do birds not get electrocuted when they land on power lines? Brilliant question. Chris?
Yes, well, the power line is, of course, at a potential. So, in other words, there's energy which is being applied to the line to raise its potential, how much, what voltage the line's running at. And for a current to flow, it's just like water. There has to be a pressure difference. There has to be a difference in the potential. So, if I take a battery, it's got a plus terminal and a minus terminal. There's a potential difference between the plus and the minus. The electrons want to come out of the minus end and go into the plus end. And the amount of pushing that they're doing determines the voltage. That's what voltage is. It's how hard the electrons are trying to move. Well, if you've got only one terminal of the battery and there's no way for the electrons to make their way to the other terminal, then no current can flow. And the thing that actually will damage you is when a current flows through you, because the current flowing through you will produce heat, and it will also affect electrically sensitive tissues like muscles, nerves and the heart. So when the birds land on a high voltage electric cable, because they're not connecting the cable to anything at a lower potential, because they're only sitting on the cable, so they're at one potential, there is no potential difference. It's a bit like saying taking a jug of water, and rather than tipping the jug so the water can come out, you just hold the jug up in the air. The water has potential, but it can't go anywhere because it's at one potential. Therefore, no current flows through the bird, and therefore it doesn't get fried. Now, what could happen, though, is if someone comes along with a kite and you're standing on the ground, so your potential is 0, and you fly your kite accidentally into the wires, then now there's potentially a connection between the wire at a very high potential and you at a very low potential, and the energy from the wire can flow as a current down your kite string, into your hand, down through you, and then into the ground. And that's why people get electrocuted when they fly kites near pylons, and you absolutely must not do it because it's very, very dangerous.
Thank you, Dr. Chris. Another question, this time about weather. We've had plenty of that. Keith has asked, he's heard that the solar wind is the weakest in 50 years. Apparently it goes in 11-year cycles. Can't we predict from that if we're going to have a bad weather and look to prepare better for it? What do you say, Chris?
Well, we do know a little bit about how the sun influences the Earth's weather patterns. And one thing that's emerged in recent years, in fact, scientists and researchers have been tracking rainfall on Earth over the last 100 years or so. And there was a paper published about a couple of years ago where scientists were measuring the levels of Lake Tanganyika and also Lake Victoria in Africa. And they were showing that the lake levels went in an 11-year cycle. And sunspots also go in 11-year cycles. And when they compared the cycle of sunspots with the cycle of the levels of water in those two lakes in Africa, they found a very strong relationship between the sunspot cycle and the levels of this water. In other words, the two were definitely and strongly correlated. And it looks like, therefore, solar activity is influencing rainfall. That doesn't sound too unlikely because there are various theories that this solar wind, this is a stream of particles and ions and charged, highly energetic particles streaming away from the sun and coming towards us through space. It's travelling about 1 million miles an hour, and when it slams into the planet's outer atmosphere, it can make the northern lights, the aurora borealis. And it's lucky for us that we have a magnetic field because this deflects the solar wind around the Earth and stops it actually turning us into a dried-out prune of a planet like Mars. But the point about solar wind is that it can also seed clouds, potentially, because some people have suggested that clouds are seeded or formed when these particles penetrate the Earth's atmosphere, and they help water molecules to coalesce around the charged particle. And once you've got one water molecule coalescing, you can get others. So it might seed clouds, and that might be therefore linked to rainfall. The thing is that it's still very, very random and variable, because although we may know that we're going to get a wet year or a drier year, we don't know where precisely, except that where things tend to get rain, they tend to get more rain, and where we get less rain, we tend to get less rain, but you can't be any more precise than that. And also, we just don't have enough data, because we've only been able to make the kinds of observations that can help in these kind of circumstances for a very short period of time. So we really don't know all the answers, and that's why we have to keep on studying it.
Now, Dr. Chris, Mike in Colchester says he was in Barbados last week. How lucky was he? Watching the blue ocean gently swaying until the waves broke and then they turned white. Why do they do that?
Water's an interesting molecule, isn't it? Because when it's a liquid, it's colourless and you can see through it, it's transparent. When we freeze it and turn it into ice crystals, if they're small ice crystals, they glint and glimmer and they look white. And when we make a spray in the sea, you get whiteness. So why is that? Well, first of all, why is the sea blue? Well, a lot of people think the sea's blue because it's reflecting the sky, but that's not actually true. The reason is that water molecules are shaped like miniature boomerangs, and they have an oxygen atom at the apex of the boomerang and then two hydrogen atoms forming the arms of the boomerang. And oxygen likes electrons a lot. It's very electronegative. So it pulls the electrons of the hydrogen towards itself a little bit. And this makes the molecule have what's called a dipole. It's polarised. So the hydrogen bits are a little bit positive and the oxygen is a bit negative. And because opposites attract, if you bring two water molecules close together, then they try and stick together. This is called hydrogen bonding, and it's why water has some of the amazing properties that it does. But when water's floating around as a mist in the atmosphere, for example, it tends to absorb energy in the infrared. So that's very long wavelength light. And so water is an excellent greenhouse gas. But when water gets into the sea and water molecules all cluster together, they all stick together with this hydrogen bonding. And this makes the molecules much stiffer because they're all glued together. And instead of absorbing infrared energy, in other words, what it was doing in the atmosphere, it means that it starts to absorb light at the red end of the spectrum. So the sea soaks up red light. Now, if you look at light coming from the sun, it's white light, and that's because it's a whole mixture of different wavelengths. And when you mix lights of lots of different colours together, you get white. But when this light that's white hits the water in the ocean, because the water molecules are all stuck together, hydrogen bonded, and they're soaking up red light, if you remove some red from the white light, it begins to look blue. And so as a result, the sea looks blue because it's subtracting red light from white light. That's giving it its blue hue. So that's why the water looks blue normally. That's why when you go underwater in a swimming pool, if you, for instance, cut yourself, maybe there's something sharp on the bottom, or when you're swimming in the sea and you cut yourself on a sharp stone or something, blood doesn't look red, it looks a funny black colour because there's no red light left in the light filtering through the sea to make the blood look red. So as a result, it looks black. But when the sea breaks in a wave spray, what you've ended up with is lots of tiny particles of water, which, when the light hits them, it scatters like a mirror. But because the particles are all tiny and they're all moving in lots of different directions and they're all irregular, the light that's being scattered off is coming off in lots of different directions, and all of the different wavelengths of light get scattered. And the same happens with snow. And as a result, you get the full spectrum of light being reflected onto your eye, and this makes it look white, just like sunlight. So that's why spray is white, snow is white. Ice crystals, on the other hand, you can see straight through, which are not scattering light, look transparent, and water itself looks transparent, but if you have enough of it, it looks blue.
That's amazing. Thank you very much. Let's welcome onto the programme now Tony. Hello, Tony.
Good evening, my lady.
Oh.
Lovely to talk to you again.
And you too as well. You're through to Dr. Chris. What's your question, Tony?
We couldn't walk on ice, obviously, but dogs and bears and all the animals can. Why don't their feet freeze up?
I think the answer, Tony, is because the dogs are walking around on the pads of their feet all the time, so they're very, very tough and thick, and they have thicker skin there. In fact, if I look at my dog's paws, then the pads that he's walking on the floor with all the time are covered in thick calluses, so he has a degree of protection there, so they don't freeze in the same way. Also, if you look at sled dogs that work in icy conditions, then their handlers do keep a very close eye on their pads because they can get frostbite if they get too cold. So they are very, very careful to keep a check on them. And sometimes they even put little shoes on the dogs to stop them getting too cold. But most of the time, the dogs are pretty resilient to it. I thought you were going to talk about things like birds and penguins.
Well, yes,
because
what about
penguins?
them?
Well, they're in trouble, aren't they? Because they have very, very skinny feet. They have webbed feet because they're birds and they're aquatic, and they use their feet like fins to propel them through the water. Why don't they freeze? Well, this problem was solved by a scientist actually at Essex University, and he found out and wrote to New Scientist magazine about the answer to this, which is that there are two mechanisms, really. One is that the blood vessels that come out of an animal's body, the penguin's body, going down the legs, the arteries going down the leg are very, very close to the veins bringing blood back from the leg. So what happens is you get what's called a counter-current exchange, where some heat passes from the cold vein, from the hot blood vessel into the cold vein, bringing blood back from the foot. And so you don't actually lose lots of heat through the feet, but by the time the blood reaches the feet, it's quite cold. But then the hemoglobin, which is what's carrying the oxygen from the lungs into the tissues, when that gives up its oxygen, that chemical reaction releases a little bit of heat. So it keeps the feet a little bit warmer than they would otherwise be, preventing them from freezing. So the bird has a clever way of preventing heat loss, but also nature's chemical reaction in which hemoglobin gives up oxygen and takes away some carbon dioxide also releases a little bit of heat, and it keeps the tissues just above the freezing point.
Good Lord, that's amazing.
Take care. Bye-bye, darling.
Yeah, bye-bye.
Bye-bye. Ewart has asked, why is it when you have an amputation you have phantom limb syndrome?
This is a major problem, and people don't often realise how serious this is until they actually get it. This is where, when you have a part of the body removed, people who have, say, a limb, a leg, hand, arm, a whole sort of half their body taken away, they will say that when they close their eyes, it's almost as though they've got the missing body part back again. They can feel it. Gosh. And not only that, it's also excruciatingly painful. And people go mad sometimes with the discomfort of this. And this is known as phantom limb pain, because obviously the limb doesn't exist. You just think it does. Your brain doesn't seem to be able to get its head around the fact, if you excuse the awful joke, that you no longer have this body part. So why might that be? Well, scientists have done a number of experiments to try and understand this phenomenon. And one theory is that the brain is obviously normally receiving signals from that part of the body. And in the same way that if you're listening to your radio and the volume drops, what you will do is reach over to the radio and you will turn the volume up and listen a bit more closely to see if you can hear what's coming out. And the brain, we think, might be doing something similar. There's a lack of messages coming in from the part of the body that's now been removed, so the brain increases the gain, the volume knob, if you like, on the signals that it is trying to pick up. They're not forthcoming, but then it begins to react to spurious nerve signals that are just noise, and it interprets them painfully. And as a result of that, you then end up with this sensation of discomfort coming from the missing body part. That's one theory. Another theory is sort of suggested by one therapy for phantom limb syndrome, which bizarrely enough involves using a mirror. And it sounds pretty basic, but what scientists have shown is that if you take someone who's got, say, phantom limb pain in their hand, say they've had their right arm amputated, if you get a mirror, you can show someone using a mirror their left arm, and because it's a mirror image, a reflection, the left arm begins to look like the right arm. So you can show someone this reflection of their left arm in the mirror, which gives them back the impression they've got their right arm, and if you ask them to do relaxing, unclenching, muscle relaxing movements with their left arm, they see the reflection, which looks like their missing right arm, doing these movements, and their pain goes away. And there was a paper in the New England Journal of Medicine about 12 months ago where they showed a dramatic improvement in patients who had this therapy, and it was persistent, it was long-lasting, and it was much better than any drug therapy. So what doctors think is that when the brain is missing a part of the body, the muscles that it thinks it's got there, it thinks it's contracting or shortening or strengthening those muscles. The muscles aren't there, but the brain invents signals as though the muscles were responding and getting shorter. And so as a result, it gets the impression that it's got a permanent cramp in that part of the body. And if you see yourself relaxing, because the visual system has projections or connections into the motor system to control it. If you see that part of your body relaxing, the visual system tells that part of the brain, which is no longer physically connected to the missing body part, that it's relaxing. It actually makes that bit of the brain relax, and as a result, the pain goes away. So it's a bit of a woolly answer because we don't really know what's going on, but we think that that's what's going on the basis of what these experiments have shown.
Wow, that's absolutely fascinating. Thank you, Chris. Now, Jill has called in and she asks, why is it that sometimes we dream in black and white and other times we dream in colour? Why not one or the other?
Yeah, it depends actually what your experiences are as you've grown up, because if you ask blind people who have been blind all their life what they dream, then they tend to say that they dream in sounds. In other words, they dream in the stimuli which are the things that they experience in their everyday life. And because they don't experience visual stimuli, they don't have any perception of vision. If you talk to people who went blind in the days of black and white television, they'll sometimes say that they'll experience a lot of black and white dreams. If you talk to people who've gone blind more recently, they say they love going to sleep because they can remember what colours are like, because they dream and they see colours again. But the thing about dreaming is that it's all about your brain basically exercising itself when you go to sleep and deciding what to chuck away and what to consolidate. We think that dreaming and sleeping is all about consolidation of useful information. It's a way of aggregating and linking and storing permanently as possible, the useful information that you've gleaned during the day. And evidence for this is that if you interrupt people's sleep patterns, then they do much worse on memory tests. And it's not just because they're tired. They don't seem to be able to transfer short-term, recently learned information into long-term memories. And so it's probable that your experiences during the day drive your dreams. You're replaying some of your experiences during the day. And if you've experienced, say, a black and white film, or you're thinking about something from the past, this may be fresh in your memory, and so it gets turned over or processed, consolidated, re-examined, replayed when you go to sleep. And that's why you may remember it in black and white. The interesting thing about sleeping and dreams is that when you go to sleep, you go through dreams when you have something called rapid eye movement sleep, REM sleep. And this occurs frequently through the night, but as the night goes on, the periods of REM sleep get longer and longer and longer, and therefore the dreams that you have get more and more detailed and complicated the longer the night goes on. So if you wake up straight after a dream, you tend to be able to remember it. So if you're having a short dream that hasn't got very complex, it might be that you've remembered the black and white one, but not the colour bits to go with it. But you tend to have your best dreams towards the end of the night, so you need to sleep really well and for a long time to have the best dreams with the most detail in them.
Interesting stuff. Well, Mark the Storman has sent an email in. He says much of science is based on what is proven, so he guesses he's asking for an opinion. But logic tells me there must be a start and an end to everything. As a planet, we, Earth, revolves around the sun in a mere pinprick of space. But does space start or end anywhere? And if it ends, what is the other side of where it ends? What does Dr. Chris believe, and what is the most plausible theory?
What we know, or the certainties about our universe that we inhabit, are that we can pretty accurately date it. We know that the universe has been in existence for almost 14 billion years, which is actually not that long, really, is it, given how vast it is? And we know that before the universe existed, then nothing was here. And it was one pinpoint, a pinprick, a singularity, a little full stop in the vastness of space, where the Big Bang happened. Space didn't exist until this occurred. There was suddenly this enormous release of energy, which turned initially a lot of heat and a lot of energy into a lot of mass, stuff, material, matter, and out of that condensed galaxies of planets and stars, and out of those condensed further galaxies and further stars and further planets, because all of the heavy elements that you find here on Earth, the carbon in our bodies, the oxygen we're breathing, has all come from stars that have lived their lives and blown themselves up. And the interesting thing about the universe that we've learned in the last 100 years or so, thanks to Edwin Hubble, after whom the Hubble telescope was named, is that the universe is getting bigger. And it's getting bigger faster the further or the older it gets. And so, in other words, the universe is blowing up like a balloon, but it's blowing up faster and faster and faster as time goes on. But the point is that the universe is everything. So if you go outside the universe, which you couldn't do, then you wouldn't exist. There wouldn't be anything, because the universe is everything. It's not expanding into anything. It's just expanding. It is. And it's really difficult to get your head around that concept. And the point is that a lot of people say, well, if we know that there's been a Big Bang and we know the universe is getting bigger, couldn't we therefore wind time backwards and find the place in space where the universe started? But the point is, because space and where it all started is the universe, it's a non-argument to say where it started, because nothing existed, so therefore there was nowhere before it got bigger. And it's this kind of spine-tinglingly difficult question that keeps cosmologists amused, and that's the kind of questions they're grappling with, because what they want to know is, at the moment, the universe is getting bigger. It's getting bigger faster the older it gets, and therefore what's the long-term consequence of that? Will we end up in a few billion years' time with a universe that's a cold, dark, lonely place because it's got so big that all the stars are so far away from us that we can no longer see them, and we're just on our own in the middle of nowhere in a cold, dark universe? Or will the universe get bigger and then for some reason begin to shrink again? Is this a sustainable expansion? Will it get to a certain size and then stop? And we just don't know the answer. And scientists are now beginning to grapple with what's actually controlling this expansion. There's this phenomenon of something called dark energy. And the really intriguing thing is that dark energy is the fabric of space that makes space expand, and the more space you make, the more dark energy you make. So it's almost like you're getting something from nowhere. And no one really understands that. And that's what scientists are trying to solve at the moment with various experiments. So I think it's going to be a very interesting time. So you just have to, unfortunately, excuse the pun, it's coming up, watch this space.
It's cosmic, darling, it's cosmic. Now, Mike in Colchester said when he was on holiday in Barbados, he was eating cereal, and as he put the spoon in his mouth, the spoon touched a filling and he got an electric shock. How awful.
Yes, what a terrific question. Why do you get an electric shock? It's exactly the same thing, and I guarantee someone listening to this will have experienced this. When you were at school, you had a pencil sharpener in your pencil case, and if you ever put the pencil sharpener, naughty, in your mouth, it will have tasted funny.
Yeah.
Have you ever done that, Sue?
Yes, I must say, yeah. It's one of those
and you get
a
funny sensation on your tongue.
Yes.
And the reason is that the pencil sharpener is made of magnesium, the blade is made of steel, it's iron, and your saliva is an electrolyte. You're making a battery in your mouth. And what chemists can tell you is that all metals have a degree of reactivity. They want to give up electrons to other things. Some metals want to do it more than others. If you pair up two chemicals, one of which likes to take electrons away from another, or one of which likes to give electrons up more than the other, then what can happen is that the more reactive thing can give up some electrons to the other chemical and produce what are called ions, and this forms a battery, a cell, a circuit, if you like. You could wire it up and make electricity. It's exactly how a battery works. Now, if you take a spoon and the spoon makes contact with your filling, you've got two different chemicals there. You've got a silver-mercury amalgam in your filling, and you've got the stainless steel spoon, it's probably stainless steel, and you've therefore got saliva, which is full of salts, which is making a nice electrical connection for you as the electrolyte, like you put in your car battery. And as a result, you get a current flowing. And the current is flowing between the spoon and your fillings, which are slowly dissolving as they react. And the taste that you get is because the electrolysis process in your saliva is producing probably a little bit of hydrogen. It may also, because there's chlorine ions washing around in your saliva, it could be producing a little bit of chlorine in your mouth as well. And these things have flavour. So you're getting an electrical tingle, and you also get a funny taste, and it's because of making a miniature battery in your mouth with your fillings.
All right, well, we've got loads and loads of questions, actually. When birds roost like pheasants, how on earth do they keep their balance in all weathers when they are asleep? We couldn't do it. Good question.
No, and it's the same question that's bothered scientists looking at animals up in the Arctic, because us animals that have a day-night cycle, because we're programmed to wake up when it gets light and go to sleep when it gets dark, unless you're nocturnal, in which case you do the reverse. That process revolves around your body clock, a collection of nerve cells in your brain. And those nerve cells get reset by light, which comes in from the sun. So in other words, you have a clock which keeps time, but it's a little bit inaccurate. So your brain has the ability, using sunlight, to reset the clock. But what about if you live north of the Arctic Circle, where 6 months of the year it's light all the time, and another 6 months of the year it's dark all the time? What do you do then? Well, scientists in Norway have been studying this, and this is Carl Arne Stokken and his colleagues, and they put radio receiver necklaces on reindeer and followed what happened to them. And they noted that these animals, just when they're in the dark phase, they will just be awake for 20 minutes and then go to sleep for 20 minutes, and they don't fall over. And the reason is that the brain has various postural centres in your brainstem which are in charge of controlling certain muscle groups. So there's an automatic system which keeps you balancing, and these brain connections control various clusters of nerve fibres in the spinal cord, turning on the neurons that control muscles in just the right way to keep your posture and keep your balance. And say you move very, very slightly on your feet, well, feedback from muscles telling the brain how long the muscle is, how much it's being stretched, go back into the spinal cord, and they trigger just the right amount of adjustment of the muscles to balance the movement so that you don't fall over. But the reflexes aren't necessarily as fast as they could be when you're awake, and as a result some people get a laugh out of running into fields in the dark and pushing animals over that are sleeping because they can't respond quickly enough to balance themselves back if you push them very hard. So it is true that you can do that, and it's a very unfortunate, very nasty thing to do. But the answer is it's all down to reflexes, and animals that are used to sleeping in that position for the reasons of safety, because if they were to lay down it would take a long time to wake up and then get up. They therefore remain standing, because that way they're already on their feet and can run away if a predator comes along. So that's why they've evolved to do that.
Yeah, it's the easiest time to move chickens if they're just having a little bit of a snooze, if you've got to move them at night. Anyway, one last one quick. Lucy in Brightlingsea says, can you tell me why minor scratches hurt lots more in cold weather rather than in warm?
I think it's probably because it's a combination of the fact that cold is painful and so is the injury. And I think when you add the two effects together, it's synergistic. In other words, the two things add up and make a powerful pain stimulus, rather than it just being painful because it's cold or painful because it's painful, you've hurt something. The same sorts of nerve fibres are involved. You have fibres called C fibres, which are very, very tiny nerve fibres. They're less than 1 micron. That's less than 1,000th of a millimetre across, these nerve fibres. And they convey pain and temperature sensation, and they connect up into your spinal cord and then inform your brain as to what's going on in different parts of your body. And I suspect that because they converge, they both connect onto the same nerve cells in the spinal cord under certain circumstances, that one can drive the other. And so you get painful stimuli from the injury site, plus you get pain from the coldness at the injury site. The two add up in the spinal cord, and you get an even bigger signal, which says to the brain, wow, this bit of the body really, really hurts now. But I don't think it's just cold, because if you've got a little cut on your finger and you put your hand under the hot tap, the bit that's hurts even more than the surrounding skin. And I think that that's probably part of the same manifestation. And the other point to add to it is that when you injure part of the body, you get inflammation locally. You get the release of various chemical mediators which make the nervous system in that area more sensitive than normal. And I think that that's also what's going on, that you get a wind-up of the nerve system there. So it's because it's trying to make you guard the injured area to protect it so it can get better. And as a result, all stimuli are interpreted as more painful or more intense than they really are while the area is injured. So I think it's a combination of those factors.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.